Electrostatics was composed primarily of 5 different ideas, 4 primary equations that we dealt with: force, field, potential, and potential energy, and then the 5th thing being Gauss's law. So let's start with the electric force, also known as Coulomb's law. One of the things to note in this equation, obviously it's on your equation sheet, the K value is 1 over 4 pi epsilon naught, where epsilon naught's a constant. And the other thing is the absolute values put around the charges, because we do not care about the signs of the charges. We're going to assign the direction of electric force based on whether the charges would attract or repel, and then their relative position to each other. Does that mean right, left, up, down? And assign positive and negative in that way. Field, we do the same thing with force with regard to the sign of charge. We are going to assign positive and negative fields based on the direction. If the field's to the left, or if it's down, we would say negative. If it's to the right, or if it's up, we would say positive. Notice that between these two equations, kq1 q2 over r squared, kq over r squared, they're the same thing with the exception of a q. So just like gravitational force equals mg, you can say the electric force equals QE. Instead of m, mass, you have Q, charge. Instead of G, gravitational field, you have E, electric field. The next is known as electric potential, more commonly known as voltage. It's KQ over R, so it looks an awful lot like the field equation. Field equation is KQ over R squared. The potential equation is KQ over R. So we just drop the square on the denominator. Voltage is a scalar, so we do not care about its direction. There is no direction. Therefore, though, we do care about the sign of the charge, being positive or negative. Electric potential energy is the continuation of electric potential, except we have a second charge present. Think about gravitational potential energy. Gravitational potential energy always depended on 2 objects with mass. 99% of the time, that second object with mass was Earth. So we didn't really worry about it, and we could just wrap it up and call it G, 9.81 down. In electric world, you can't do that. You have to care about both charges. Again, in the gravity world, you had the mass of your object in question, and then the mass of the Earth was already accounted for in G. Remind you that G, little g, actually equals big G times m over r squared. So the mass of the Earth was accounted for in that. Notice again, voltage is kq over r, energy is kq1 q2 over r. Just like voltage, this is a scalar. We do not care about the direction, but we do care about the signs of the charges. In general, what you can say is if solving the energy, the potential energy between 2 charges comes out negative, it means they're attracting each other. And if it comes out positive, it means that they are repelling each other. The last thing is Gauss's law. Gauss's law is used to determine the electric flux passing through a given area. This is, if I had to take a guess on what the AP is going to be doing, what the College Board is going to be doing, this one's huge. Knowing Gauss's law is going to be a big deal. So as you study your electrostatics, make sure that you got this one down. Especially since there's no magnetism, I can't imagine that they would not have Gauss's law involved in this. And we can go through some practice problems too, leading up to this exam. The other thing I did want to point out is how field lines and electric potential lines relate to each other. So on the left we have a positive charge, and we see that the field lines are pointing away from it. Those concentric circles you see around are the equipotential lines. So everywhere on, say, for example, this outer line here, everywhere along that outer circle has the same potential. The other thing to note is that the equipotential lines are perpendicular to the electric field lines. And our final review will be circuits.